final week of this course on Newtonian mechanics with examples. Let us start with a very interesting concept called principal axis of rotation. So, remember that when we discussed the moment of inertia which is required to understand rotation, we said our goal is to go through to be able to solve two kinds of problems, and so far in the previous week we discussed the first type of problem, which is that given a mass distribution of an extended object and a set of axes of rotation, compute different components of moment of inertia with respect to the x axis, y axis, z axis, which sort of give you that how much is the spread of the mass distribution about those axes of rotation. And the second is to compute the products of inertia, which we considered in the previous lecture, and we saw that this quantity gives us the so if this is 0, this means that the mass distribution is symmetric about that axis, and if it is non-zero, then that means the mass distribution is asymmetric about that axis. We have considered several examples in the last week of like where the reference axis, so the origin was taken at the center of mass for some and the axis of rotation were the symmetrical axis of symmetry of the object. We also generalized this the moment of inertia, and we now know that we do not have to take only the axis of rotation or only origin at the center of mass. We can put the origin at arbitrary location and choose arbitrary axis of coordinate system, and even then we now able to calculate the components of moment of inertia. Today our goal is to look at the second type of problem, which is given a mass distribution of an extended object, find the principal axis of rotation. So, let us start by understanding what is this principal axis of an extended object. So, we take a two-dimensional mass distribution because it is easy to visualize it in 2D. So, we take example in 2D. So, this rectangle is a rectangular mass distribution. Now, we are showing two different coordinate system, the black and the blue. Now, in the left figure, these two coordinate system are the orientations are parallel to each other, but the origins are different. So, you can translate the one coordinate system by some fixed along this particular direction, and then you can go to the next coordinate system. In the right hand figure, the origins are same, and then if you want to convert from the black to blue coordinate system or vice versa, you have to do a rotation. So, in the left figure you have to do a translation, and the right figure you have to do a rotation. Now, clearly if we look at the, so let us say if I extend this figure a little bit, it is clear that the black reference frame, black coordinate system is a reference frame in which the mass distribution is symmetric about the origin, whereas the blue reference frame in both the figures, the mass distribution is asymmetric about origin in both the case. So, here we pose a mathematical question. We ask what is the coordinate transformation rule. So, in specifically let us say if we take the right hand figure, so how much is the rotation we have to give by an angle theta. So, to go from the asymmetric coordinate system to symmetric coordinate system. So, to go from the blue to black or black to blue vice versa. So, we have to rotate by some angle theta, and in this particular case the axis of rotation is the z axis, which is perpendicular to the plane of the figure. So, about the z axis we have to rotate by angle theta to go from one coordinate system to another coordinate system. Question is, how much is the theta? Now, before we go to that problem, so let us first write down what are the components of the moment of inertia in the asymmetric coordinate system. So, if we take any point dm which is located at a coordinate xy, so this is, so if I drop a perpendicular, then this is y, this is x, and if I draw a perpendicular, this is y. So, then a mass element dm and rho is the density, and let us set rho to be 1. So, we omit the density. Then by now we know that this integral y, this area double integral y squared times dA, dA is the area element which is dx times dy. So, y squared times dx times dA gives you the moment of inertia about this particular x coordinate. So, the moment of inertia of this object with respect to this x axis. So, with respect to this axis, if I calculate the moment of inertia, that will be Ixx, and similarly if I calculate this particular integral x squared dA about the y axis, that will give me the moment of inertia about this particular y axis. And similarly, if we calculate the product xy times dA, that will give me the Ixy. So, by figure it is clear that this particular choice of axis, the mass distribution is not symmetric about this particular choice of axis. So, we expect by definition that this Ixy to be non-zero. Now, we can do the same thing for the black coordinate system, which is symmetry, in which the mass distribution is symmetric. So, by symmetry, the middle point of this rectangular is the center of mass, and this is clearly passing through the center of mass. Here also the axis is passing through the center of mass, but the orientations are such that the mass distribution is asymmetric. Here the orientation of the axis are such that the mass distribution is symmetric. So, again we can write down the components in this black coordinate system. So, I take the same element here dm. So, the mass is a scalar, does not change if you change the coordinate system. Now, this coordinate, but now the coordinates, the position vector is now different. Now, its component are x prime and y prime, which is different from components are different, point is same, but the components are different. So, now this is your x prime and this much is y prime, but the area remains the same. So, this is a property of the coordinate transformation, that the area will remains the same. So, I am going to assume this result. Those of you who are interested, you will encounter. So, you have to calculate something called Jacobian of this coordinate transformation, and you can easily show that the Jacobian is 1. So, that the area will remain the same. Now, by we apply the same definition. So, now if I take this x axis, then the moment of inertia about this axis will be given by I x prime, and moment of inertia about this y axis will be given by I y prime, and the product of inertia will be given by this particular quantity x prime y prime dA. And since we see clearly that the mass distribution is symmetric about this axis, we expect that the product of inertia should be 0. Now, in this case, this is easy to see by doing this integral. So, say that when I do this integral x prime y prime dA, now if I keep y fixed, x fixed, and then for this dm element I take its reflection about x axis, that is x prime axis, and this is the reflection. So, it is the image of this element. So, the difference is that this has the same distance from x axis, but a sign is different, then the contribution to this area and this area will have equal magnitude, but opposite in sign. So, for both of them x prime is the same, but y prime is equal and opposite in sign. So, if we add them, they will cancel each other, and similarly if I do it over this 1/4 of this distribution, we can easily see that this 1/4 of the distribution is going to cancel the lower 1/4 of this distribution. Hence, and similarly this part of the distribution is going to cancel this part of the distribution, and hence we see that this I x prime y prime is expected to be 0. So, you can actually work it out. So, let me work it out. So, when I do x prime y prime dx dy, since this is a x and y in this particular case is a rectangular distribution. So, x and y are independent. So, this is x prime y prime times y prime dy prime. Now, let us say that this length is a and this side is b. So, this is a by 2 to, so x varies from minus a by 2 to plus a by 2 and y varies from minus b by 2 to plus b by 2. So, the limits are minus b by 2 to plus b by 2. So, this gives me x square by 2 a by 2 to minus a by 2 times y square by 2 b by 2 to b by minus b by 2, and this is 0 into 0, which is 0. So, you now verify that if I x prime y prime the product of inertia is 0, then the mass distribution is symmetric. So, this is what we just checked, that if mass distribution is symmetric about the origin, then the product of inertia is 0 in that reference frame. So, this is the key idea to understand the principal axis of rotation. So, what we need is that here, so suppose in this case it is easy to guess what is this axis of symmetry, the choice of axis for which the mass distribution is symmetric. But suppose we have some complicated shape of the object, so that it is not easy to guess what is the axis, the choice of axis about which the mass distribution will be symmetric. So, what we can do, we can start with arbitrary axis such as this blue axis and calculate the moment of inertia. Then we can ask this question that how does the different components of moment of inertia will change under rotation when I go from blue axis to black axis, that is under a rotation by an angle theta about z axis. Now, I am going to give you the answer, and the answer is here. So, this is some transformation formulas. So, if we know the components of the moment of inertia Ixx, Iyy and Ixy in the blue axis. So, blue is asymmetric and black is symmetric. So, if we know the components in the blue axis, then we can calculate the components that will be in the black axis by using this particular formula. So, here is our first lesson, that even if we have the same object and same origin, but still the moment of inertia is not unique. So, this is something you should remember, depends on our choice of the axis or choice of the reference frame. So, then we can sort of say that, so now we are going to use that particular principle, the particular idea, that if the in the black axis the mass distribution is symmetric, then the product of inertia must be 0. So, you can use this condition to calculate the value of the theta. So, note that the right hand side depends on the components in the black axis, the blue axis, as well as the angle of rotation theta. Then we can demand, so this is a very interesting part of this particular formula. So, I am going to show you, give you the result. So, now if we demand that this product of inertia is 0, which is the condition that our black axis the mass distribution is symmetric, then you demand this is equal to 0, you can easily show to solve it for the value of alpha theta, and the particular solution is alpha. So, theta equal to alpha, which is given by this particular relation between the components. Very interestingly, turns out that we can also, is the same condition if we ask a slightly different question. So, the second question is, in which reference frame the moments of inertia have the maximum and minimum values, which means in which reference frame the Ixx and Iyy are maximum. So, what do you mean by that? So, as you can see that the moment of inertia depends on the choice of axis. Now, if you take different values of theta, you can generate, starting from your blue reference frame, you can generate different infinite number of different possible choice of axis, and in each of those reference frames you can compute the moment of inertia of the given same object. Now, you can ask that which frame will give me the highest value of the moments of inertia, and it turns out that you not only get the highest value, but you also get the lowest value in the same frame. So, the condition is that if you take this d I x prime, and so this is a function of theta. Now, if you extremize this with respect to theta, so if you calculate the derivative with respect to theta and set it to 0, that is the condition of maximum or minimum, then you end up with the same value, that is the same condition that gives you the I x prime y prime to be 0, also gives you, there is the same condition that gives you the I x prime and I y prime to be maximum, which means that the moment of inertia is maximum and minimum in that particular reference frame in which the mass distribution is symmetric about origin. So, it looks like there is a certain special, given an object and some particular origin, there is a certain special reference frame in which has two interesting property. The first property is that the mass distribution is symmetric about the axis in that reference frame, and the second property is the moments of inertia have the largest and the lowest possible values. So, this particular set of reference frame is called the principal axis of rotation. It is a special, given an object, it is a property of the object that you can always define a particular reference frame in which the mass distribution is symmetric. So, no matter what is an object can be very highly irregular, but it always has a particular choice of axis of symmetry. And here I write down the value. So, if you plug in this condition that this tan to alpha is using this condition, and in this particular equation you can derive this formula. So, I put it as a take home exercise to work out the algebra. It is just 2-3 lines of algebra. So, you can see that this is of the form a plus b and a minus b. So, this must be the maximum value. So, note that the second term is the same in both the equations, and the second term is always a positive quantity. So, this must be maximum and this must be minimum values of the moment of inertia. So, now the question is that this is fine. So, we appreciate that there is a given object, there is always some axis of symmetry, fine, and then there is, if you want to calculate the moments of inertia about that particular axis, we have this particular complicated set of formula. And but now another beautiful thing is that you do not have to remember this particular complicated set of formula. You have to remember just one rule, and this is the following, that here we are going to use the full power of vector and matrix algebra. So, we are going to represent the moment of inertia as a matrix. So, in 2D we are going to write the different we have three different components, Ixx, Iyy and Ixy. So, we are going to arrange them in a 2 by 2 matrix in this particular order, and the fourth element Iyx will be by definition this. So, this is symmetrical. So, we have a 2 by 2 matrix in 2D. So, the point is that if we take an arbitrary reference frame, if we do not know what is the axis of symmetry, we can allow to take an arbitrary reference frame, then in general these two components are non-zero, and if we are computing these components in the symmetry axis of about the axis of symmetry, then these two components are 0. Now, here we recall what we learnt in the first week of this course, that we discussed several different ways of defining vector, and we introduced the most general way of defining vector is that how it behaves under a coordinate transformation, such as under a rotation by an angle theta about z axis. And we show that the vectors are quantities such as the position vector is that if you take a, so this matrix represents the rotation by an angle theta, counterclockwise rotation by an angle theta about the z axis. So, we start from this some particular choice of axis, and then this is our y prime and this angle is theta. Now, this geometrical operation we can represent it by this particular 2 by 2 matrix. Then the question is, so this is about the vectors which can be represented by a column vector. Now, what about a 2 by 2 matrix? How does a component of matrix changes under the same transformation? So, here I am just going to state the rule, and this rule is particularly easy to remember. So, this is the rule: you take the matrix which is your 2 by 2 matrix, and then you multiply on the left by this same rotation matrix R, which is a function of theta, and from the right hand side the transpose of the rotation. So, this is called the rotation operator. So, this is hits this matrix and rotate it coordinate system by an angle theta. So, then you can easily, so I will give it again as an exercise to you to verify. You can check for yourself that if you take this particular matrix or the product of these three matrices, you get exactly the same formula as listed here. So, you do not have to remember this complicated looking formula, you just have to remember a following fact, that the moment of inertia in 2D is a 2 by 2 matrix of this particular, where the elements are arranged, diagonal elements are the moments of inertia about the axis, and off diagonal elements are the products of inertia, and then this is the rotation operator. So, this is the rotation operator, and then the transformation rule is multiply from the left hand side by R and multiply from the right hand side by transpose of R. So, the objects in general of mathematical quantities that follow this particular transformation rule are called tensor of rank 2. So, that is why we discussed this particular way of defining scalars, vectors and tensors in the first week, so that we can now use it. So, this is something you should remember, that moment of inertia is just not a single number, it is a matrix, and a matrix is a tensor of rank 2. It is not just a simple quantity with a magnitude and direction, it is much more complicated than that. So, physical meaning will be clear in the coming lectures. So, then finding the principal axis of rotation we can pose now as a problem of matrix. So, we demand that suppose we started this matrix and we demand that we want to go to do some transformation on this matrix, so that it become the off diagonal elements become 0. That means, we are talking about matrix diagonalization. So, now this is a standard problem in linear algebra, how to diagonalize matrix. There are two steps. The first step is to find the eigenvalues. So, you take this matrix and suppose lambda is an eigenvalue of the matrix. So, it satisfies this particular equation, that Ixx, Ixy, Ix, Iyy times some particular vector which we denote as x times y is lambda times the same vector. So, this is the eigenvalue and this vector is called the eigenvector. So, in order to get the eigenvalue and eigenvector, so if we take both take this quantity on the right hand side, we get Ixx minus lambda Ixy, Iyx, Iyy minus lambda times xy equal to 0, and this will be true if this determinant of this particular matrix is 0, and hence this is the condition I have written here. And then if you take the product of the apply the determinant formula, you get this equation. Now, this equation I write in terms of word to emphasize that if you expand this, you get a quadratic equation where the coefficient of lambda is 1, the coefficient of lambda square is 1, and coefficient of lambda is this particular so there is a mistake, there is no by 2. So, is the trace which is an invariant under the transformation. It is a property of the matrix that if we take this transformation by rotation by angle theta, trace remains the same, and the other quantity will be this particular combination which is called the determinant of this matrix, which is another invariant. So, this trace and they are invariant under the rotation. So, then we can solve this quadratic equation and write down these eigenvalues. So, we get there is a quadratic equation. So, we have two possible eigenvalues, and now you can see that these two eigenvalues are precisely the moments of inertia of the object in a symmetric, in the axis of symmetry, about the axis of symmetry. So, to summarize, what we need to do is that, so this is the first step, and the second step is to find for a given eigenvalue, then we need to find the eigenvector. So, the eigenvector, so this is this particular vector. So, once we find this eigenvector, this will constitute the this will give us the direction of the, so this direction. Now, if you take an eigenvector of magnitude 1, this will give us the direction of the principal axis of rotation. So, this is the procedure. Now, the power of this particular method of thinking of the moment of inertia as a matrix is that we can now easily generalize it to 3 dimension. The only difference will be that in 3 dimension the moment of inertia is a 3 by 3 matrix instead of a 2 by 2 matrix. This is the only difference. The rest of the procedure is the same, that you take the matrix, so you choose any arbitrary. So, to summarize, what we learned is that given an object 2D, 3D, 1D does not matter, any dimension, given an object there always exists a axis of symmetry. These are called the principal axis of rotation. I mean, if the object is irregular shaped, then it is not obvious just by looking what is the principal axis of rotation. So, the procedure that we learned is that you first compute the moment of inertia components along any particular arbitrary choice of axis, and then you find the eigenvalue and eigenvectors of that moment of inertia. So, the eigenvectors will represent the direction of the principal axis of rotation, and this procedure is very powerful, very general, and works in all dimensions. Thank you.